Okay, so I'm gonna try to make up for the time lost. So we discussed what lambda meant. Right? Lambda meant it had boosts, rotations, actually parity, time reversal. And in particular, we're going to focus on the first two, because these are the continuous transformations. And as you might guess, just like the rotation group, what we're going to do is we're going to try to write down this exponential form, right? And that's where that's where the Lie algebra, the analysis of Lie algebra is going to come in. So lambda, which is by the way, the Lorentz transformation matrix. So let me write out the indices explicitly. We expect to be an exponential, and I'm going to just write it down explicitly, of x. Later on, I'm going to write down explicitly in terms of a superposition over, I'm going to show, okay, I'm going to show that this x is going to be e to the minus I over 2 omega mu nu j mu nu. I'll use alpha beta, mu nu. Okay. And so we're going to build this up, but these generators will be the generalization of the rotation group, and we'll see how it goes. Okay, so in fact, what we're going to do is we're going to study the small transformations to figure out what the property of x would be. But remember that this is always possible because we are focusing on boosts and rotations, in which we can claim is continuously connected to the identity. Right? In this case, it's a 4x4 identity matrix, or D by D identity matrix. And because of that, we can always claim that it's always expressible as an exponential. And so let's plug this in. Remember, it's lambda mu alpha, lambda mu beta, beta mu nu equals to beta alpha beta. That's the fundamental, the defining property of what the Lorentz group is. So let's plug this in. So e to the x mu alpha, eta mu nu, e to the x, nu beta must be equals to eta alpha beta. And so for small transformations, it means that I can now start to expand, Taylor expand this guy. Okay, so it's 1, the identity, plus, in fact, 1 identity plus x plus higher order terms mu alpha, eta mu nu, and then 1 plus x plus higher order terms mu beta equals to eta alpha beta. Okay, so of course the identity, the mu alpha component of the identity is of course nothing but the connected delta mu alpha plus x mu alpha, or I should say also, because we're now doing flat space time as opposed to flat space, there's now a metric that is in my convention eta. Is 1 minus 1 minus 1 and so on. There is a sign difference between the time and the space part of the metric. So it's important to keep that in mind because the placement of the metric, placement of the indices depends on the metric, right? So if you want to move your indices up, you have to use the inverse metric. If you want to move your indices down, you need to use the metric. And so it's important to keep track of where your indices are. Okay. Anyway, I just want to mention that before we continue. In fact, I'm about to move my indices. So, so you'll see what I mean. This is Kronecker nu beta plus x nu beta plus higher order terms equals to eta alpha beta. Okay. And now, this will be if I just contract these guys with eta. What do I get? I get eta mu alpha contracted delta Kronecker mu alpha contracted with Kronecker mu nu gives me alpha nu plus x. Now all I'm doing is when I contract x mu alpha with mu eta mu nu. Now this is just moving the index mu from upstairs to downstairs and then putting a nu here. Okay, so it's x nu alpha downstairs. This is quite crucial because quite crucial to keep track of where the indices are. And then now I have Kronecker nu beta plus x nu beta and higher order terms equals to eta alpha beta. Okay, let's keep going. And so I just want it to be small. I want to focus on the small transformation case. So I'm going to be content with just working this guy out up to first order in x. Right? I'm cheating a little bit in the sense that I know what I expect. Right? It needs to be a superposition over the generators. So I'm not going to prove that going up to first order is sufficient. In fact, physics books don't justify that usually either. So I'm just as sloppy as the rest of the books. But in some cases, you can, in fact, justify it more rigorously. So, for example, when we talk about SL2C, I will, in fact, show you can construct the matrices in an exact way without resorting to this kind of infinitesimal arguments. But anyway, let's keep pressing on. The results are well known, so I don't think we are in any worry that this is somehow wrong. So so let's do it to first order in x. So this is zeroth order, eta with Kronecker. This will give me Kronecker, eta alpha beta. And then this guy with this guy would be the first order in x. And remember that's a metric, this is x, so I'm just going to move the index nu downstairs and I'm going to put a alpha. So it'll be x alpha beta. And then x contracted with these guys gives you what? This gives you first order in x, but this guy will give you second order in x, so you don't really care. So really it's just this guy and this guy. You can also say, right, these dots are higher orders, so when you contract with these guys, you don't care as well. Okay, so basically you have up to first order in X, you have the following. And so, of course, eta alpha beta cancels eta alpha beta on both sides. Actually, let me not cancel. I just want to leave a clean calculation so that you guys can follow what I'm doing. So if you cancel it out on both sides, then what do you get? You get x alpha beta at with both lower indices is actually an anti-symmetric object. Okay. That's the key result that we have derived. That the exponent of lambda must be an anti-symmetric guy if you write the indices downstairs for both both of them. It's very crucial that it's both downstairs or both upstairs. You can't have x up, alpha up, beta down, and that's a different object. Okay. So let me write it down in words. So i.e. x alpha beta is anti-symmetric. That should sound a little bit familiar, by the way, because if you remember, that's exactly the result we got for rotations. We discovered that the rotation matrix can also be written in an exponential form. And when we asked the question, what is the most general x? The most general x for the rotation matrix is also an anti-symmetric matrix. The key difference between the Lorentz group that we're studying here and the rotation group is that this guy is anti-symmetric if you lower the indices. Okay? Whereas there's no such issue with the rotation. And why? Because in rotation group, you're just dealing with flat space. And in flat space, if you use Cartesian coordinates, eta mu is replaced with Kronecker ij. And then there's just no issue. It's just either 0 or 1 when you move your indices. And 0 or 1 means you don't, nothing to worry about. So, in fact, I've just managed to show this guy. But let me write it down more explicitly. Any questions? Okay, don't be shy. Okay. The other difference with the rotation group, which is a mistake, I just realized a typo I made in my notes, is that in the rotation group we superpose we factored out an I, so the anti-symmetric guy became a Hermitian object, and then we superpose over these Hermitian objects using real numbers, and of course these real numbers are just rotation angles. Okay, but it will turn out for what we're going to see quite soon. That for the Lorentz group, the superposition over anti-symmetric guys will in fact involve, in general, complex numbers, right? Not real numbers. And so while the rotation is orthogonal, you would like to think that, maybe lambda would be unitary, right? What is the analog of that? It's not even unitary. It's not orthogonal for sure. It's not even unitary. So this has some impact, in fact a lot of impact on the representations of the group. Okay, what kind of, how do you get unitary operators from the Lorentz group is an issue. So we'll discuss this as we go along. But let's write it down. So to get the most general anti-symmetric guy, you therefore superpose over the basis, right? And so basically x is now minus I omega alpha beta j alpha beta. And these guys are the basis antisymmetric. Let me write it down. Let's call it sigma rho, right? Because I'm now okay, maybe I'll use sigma rho. Sigma rho here, sigma rho here, and now I'm asking what's the most general x alpha beta? So the answer is that the most general x alpha beta is just the sum over the basis antisymmetric matrices. Okay. And how do we do that? We in fact demand that minus I j sigma rho alpha beta must give you, so right now these guys are just numbers, okay? And like I said, these are complex numbers. These guys are complex numbers, okay? And because we want to allow the most general superposition. So yeah, how do we get the most general antisymmetric matrix? This guy must be, I claim, Kronecker, one such basis is Kronecker sigma alpha, Kronecker rho beta, and let's antisymmetrize the alpha beta. And so this guy, I'm going a little bit faster only because this guy is exactly the analog of the rotation, the construction for the rotation matrix. Okay, so in the rotation matrix, we also wanted antisymmetric basis of antisymmetric matrices. So, for example, in 2D, there's only one choice: 1 minus 1, 0, 0. Up to a normalization, of course. There's only one choice. In 3D, you have more, right? You have 0, 1, minus 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, minus 1, and then finally 0, 0, 0, 0, 0, 1, minus 1, 0, 0. Basically, just choose which component in the upper triangular matrix do you want it to be 1, right? Once you choose that to be 1, the corresponding element in the lower triangular entry must be minus 1. And then just set everyone else to be 0. And then you just have as many basis matrices as you have upper triangular components. So in fact, there's no difference between, at this level, there's really no difference between what I'm doing here and the rotation group, because it's just matrix algebra. I just want the most general antisymmetric object. Okay. So for example, in 4D, this is, so now I can think of this as 1 plus 1 dimension. 1 time 1 space. This is 1 time plus 2 space. Right? I said this is rotation. But as far as matrices are concerned, there's no difference. Right? As long as I'm talking about the lower index object. So again, I can think of this as 1 plus 1 dimensional space-time or 2D space. 1 plus 2 or 3D space, and so on. So by the time I get to 4D, for example, let's count. Okay, let's count how many basis antisymmetric matrices. And the answer is as many as the upper triangular components. And so let's just count. So if you're in d dimensions, then the matrix is d by d. So d squared. And then you subtract off the diagonal components. This will be d. And then you divide by 2. Okay? Which is d minus 1 over 2. So for example, in the most important case where d equals to 4, you have 4 over 2, which is 2, times 4 minus 1 is 3, and you have 6. You have 6. Okay. 6 independent bases. And therefore, when you superpose over these guys, you will have, in principle, 6 independent parameters. Okay, 6 independent parameters. And we'll see what they mean. Okay, we'll see what they mean. We'll see what they mean. In fact, let's do it. Okay, so, for simplicity, let us work in two plus one dimensions, 2 space and 1 time. Okay, and the reason for doing that is because I don't have so many matrices to deal with. Okay, so in fact, you can already guess. So in fact, so in this case, we'll study rotations and boosts separately. Okay. And for 2 plus 1, it's simple because for rotations, you don't have a choice, right? You have a 2-dimensional space and one time. And so as far as rotations are concerned, you don't have a choice because the only possibility is given by the following. You leave time alone, and then this guy is in fact the rotation matrix. Because by 2 dimensions, you can write down explicitly is 1 and then cosine theta minus sine theta, cos theta. Right. So meaning you're just rotating the 1-2 axis of your space-time. But we already know how to calculate this. This is in fact, if you remember, 1, and then this guy itself, you recall, is the exponential of theta minus theta times the generator. 1 minus 1, 0, 0. Okay. You can check me on this, but we computed this, in fact. Okay, this guy, which means you can now promote it to space-time, and what you'll discover is that this is nothing but the exponential of minus theta of just promote this to 3 dimensions. So it'll be 0, 0, and then it will be 0. And then here will be minus 1, 1, 0, 0, 0, 0. Okay. Like I said, all I'm doing is just promoting the analysis that we did in for rotations in 2D to 2 plus 1 dimensions. Okay. But of course, what we have done is more than that. We in fact usually pull out an I, so therefore we put an I here, and as a result we put in a minus I plus I here. So that this is now a permission this is now a permission matrix. In fact, sorry, I don't like to do this. I don't like to modify my equations midway. So just to make it clear, what I'm doing 1 minus 1, and then to pull out to make it look like that, I get e to the minus I theta, and then the matrix now becomes permission 0, 0, 0, 0, 0, minus I, 0, 0. Okay. So for rotations, the generator, so to speak, this guy, which is, by the way, J1, 2. Right? There's no choice. When it comes to rotations, there's no choice. Because there's only one plane you can rotate. For boost, there are two. So we'll see how, in fact, let's see how that works out. Oh, I should be a bit careful, of course. This is the matrix, but now this is mu nu. This matrix occurs in the exponential of this operator, rotation operator. And the rotation operator has one up and one downstairs index, right? So I have to be a little bit careful when I say this. I should be careful that the exponent now has also one up and one down index because of the way you multiply matrices. So I have to be a little bit careful. But in this case, it's still antisymmetric because we're talking about rotation. But now I have to be a little bit more careful because I'm going to move on to talk about boosts. Yeah, again, that is the case for rotations, and now for boosts. Okay. And so for boosts, I'm just going to call it lambda of c, and I'm going to write it down into the e to the I over 2 omega alpha beta, j alpha beta. And I'm going to try to figure out what this mean by looking at specific examples, because I think that in this case it's much easier to see what's going on. So let's talk about boost in the first axis. So remember that we actually talk about the boost in 1 plus 1 dimensions. In 1 plus 1 dimensions, it's actually very easy to write down the most general boost. Is actually a generalization of rotations. It's actually cosh C, sinh C, cosh C. And C here runs over the real line. By the way, this is called, I believe, rapidity. And the reason why it is useful, number one, it's completely general, right? So if you learn special relativity, you probably only learn the case where you boost a time-like vector to the rest frame, or you boost it from the rest frame to some time-like vector. Maybe you talk about the null case. You hardly talk about space-like case, right? So for example, it is a true fact that we seldom talk about at least in introductory physics, special relativity classes, right? Which is that if you have a space-like vector, you can always boost it so that the components are have no time that's an example. This is actually something that is contained within this general expression. Number two, it obeys a clean multiplication rule, very much like rotations in 2 dimensions. So in rotations in 2 dimensions, when you multiply 2 matrices, 2 rotation matrices, you know that in 2 dimensions it's very clean. It's just a sum of the angles. Okay? And in fact, if you remember, we made an analogy between this and the circle on the complex plane. Okay? Because multiplication by a complex face on the complex plane is basically rotation by phi. And so there is, in fact, a direct map between rotation on the 2-dimensional plane to the complex number, the complex plane, in fact, the circle on the complex plane. Likewise, for boosts, you can calculate quite directly in 2 dimensions. When you boost and then you boost again, the total boost is just the sum. This involves the sum of the rapidities. Right? So the nice properties about this, although we don't use it that much, right? In special relativity courses, probably you've seen it. Maybe your professor writes it down for one time, and then you never see it again. But turns out that this representation will be very useful for what we're going to try to do, which is the following, right? So boost in the one direction, which let me call it C, not C, lambda 1 of C is now the generalization of this. So this mixes the time and first direction, but the second direction, I'm not changing it because by assumption, I'm only boosting in the one direction. So that's the boost matrix. But you can look at what this is. In fact, this is just exponential of C of 1, 1, 0, 0. Okay, how do I know? Because just take a expand this. Lambda of C is lambda of 0 plus lambda prime of 0 times C plus higher order term. Right? Lambda of 0 is, of course, just the identity. The first order term is C, and then if you take a derivative, you discover these guys will be 0 because they become sinh at 0, 0, and the sinh on the off diagonals become push, which is 1, 1, 0, 0. Okay. So very easy to work out. Once you know that this is the expected form of your boost matrix is the exponential or something linear in C, then you can just tailor expand to read off what the matrix is. So that means that this guy, right away, we can figure out what this is. This is exponential of C. And then now, the only tricky part is that this was 1 plus 1, this is 2 plus 1. So therefore, you get now 0, 1, 1, 0. And then the rest of them are 0, 0, 0, 0, 0, 0. Because you're not touching the rest of the components. And so to make it look like what we were trying to do, which is that, let's pull out a minus I. Okay, so exponential of minus I C, and then we have now, remember, we pull out minus I, so you must multiply by I throughout. So you get I, 0, 0, 0, 0, 0, 0, 0. And so you see now there is a stark difference between the generator of boost. So what is this? This is now, remember, this is the non-zero component, by the way, as you remember, is the label for alpha beta. So here, alpha beta is actually 0, 1. So this is J01. And the stark difference is that J01, unlike my J12, is not permission. This guy's permission. You can see it right away. The only thing it is symmetric, right? When you take its dagger, you find it's actually anti-permission. So there is a stark difference between the generator of rotations and the generator of boosts. So this is permission. But this is actually anti-permission. So I heard the bell, so I better hurry up a little bit. So let me write down the boost in the second direction. So boost in second direction is you leave the first space component intact, and then you mix time and the second space component. This one is this, and then again by generalizing this, you see that this is just e to the c of, remember, just take and expand this thing, and so you get 0, 0, 0, 0, 0, everywhere is 0, except this. Okay, and again, if you pull out a minus I, then it gives you e to the minus I c, and then I 0, 0, 0, 0, 0, 0, 0. Okay, that's this matrix is J 1, 0, 2. Okay, and this is again anti-permission. Remember the formula. The number of generators is d times d minus 1 over 2. So in 3 dimensions, it's 3 over 2. 3 minus 1 is 2, and you have 3 generators. But now we have additional insight to what these 3 guys are. In 3 dimensions, the one of them, 1 out of 3, is the rotation generator. The J space component is the rotation. And then the other 2 are the boosts. J with time space is the boost in that particular time, space direction. So J01 is the boost in the one direction, and J02 is the boost in the second direction. Right, and again, remember that the superscript denotes which component in the upper triangular part of the matrix is non-zero. Right, that's how we label these guys. And remember, the way we reckon it, these guys are 1 up and 1 down. Right, so this is mu, this is mu. The generators also have indices with 1 up and 1 down as index, but I just want to suppress them because I just want to show you what the matrices themselves look like. So we have an interesting situation in the following sense. When we do quantum mechanics, we're used to the rotation generators. We call it angular momentum, right? Actually, angular momentum is just nothing but the generator of rotations. That's the more powerful and more general way to look at what we're doing in quantum mechanics. But now, we discovered something interesting. When we now incorporate special relativity, we discover that the generator of boosts is not Hermitian. Okay? And this will have some consequences for the physics that we want to do. In particular, you discover that the superposition over these matrices, that's why they involve complex numbers. We'll discover, for example, certainly in the case where we do SL2C, the generalization of this to more abstract versions of the Lorentz transformation will bring us to some objects that are quite unusual in the sense that it's unintuitive and we don't see it. I think we should see it more often, but we don't see it so often until we take a class like quantum field theory. Okay. Any questions for me? No? Everyone is so quiet. Okay, don't be shy, okay? You should ask questions. I'll see you guys tomorrow. I always forget tomorrow, yeah. Okay.